That's okay. I speak loud enough. I don't need a microphone. Okay. So basically, Professor Chen is actually he's a hometown boy. He graduated from NTU. Then he went to Columbia to receive his master's in mechanical engineering. Eventually, his doctoral degree from Columbia. Okay. And then he came back home, and now he actually is a full professor at the Department of Engineering Science. Okay, at the same institution. And where he's also a big shot, the director of the Center for Micro, Nano Science and Technology. If you ever go to Taiwan, you should definitely visit that center. It has a lot of money, got many, many $1 million of institute, and he's the boss, he's the head of that center. Okay. So today he's actually going to tell us a little bit about how to do temporal focusing, multiphoton microscopy for bioimaging and also microprocessing. Okay, let's welcome Professor Cheng.
Thank you, Director, and thank Professor Dong introduction. Also, thanks for Professor Chen inviting me here. And I'm Shean-Jen Chen, and from the Colloquia Department of Engineering Science. So today's topic is multiphoton excitation microscopy, and also use the multiphoton induced laser operation. But the technique is based on the temporal focusing. It's very slightly different to the conventional femtosecond laser system, point by point scaling. But I will talk about detail. Okay, this is a conventional femtosecond laser. I just mentioned you need to use the high NA objective, and you have the colorimeter to control the x-axis and the y-axis to point by point scan. Then you can get the 2D image. Then you can move your stage to get the 3D image. This is a conventional femtosecond laser, so can provide you the molecular image such as the two-photon excitation fluorescence, or second harmonic generation image, or the fluorescence lifetime image microscopy. In our system, we also add the acoustic optical modulator to control the laser on and off. So we can base on the AutoCAD, the 3D modeling design, and so slicing your modeling to the 2D the process pattern. So you can do the laser operation or the 3D lithography based on the multiphoton system. So in the biomedical nonlinear microscope, so you can use a long wavelength, the near infrared photon. So simultaneously the electron can absorb the two photons and emit the short the fluorescence. So can provide you, like here is the dendrite spike for the two photon excite fluorescence. So you can look at the dendrite and the spider. The spike size is around 500 nanometer. So you not just for the fluorescence signal, you also can provide you for the second harmonic, like the chicken tendon, the collagen. So you can see the collagen image. And because you use the long wavelength, so simultaneously you will not just excite the one fluorescence, you can excite the multi-fluorescence, the kind of multi-color image. The moreover, you can not just use a two photon, you can use a four photon. Just like if you increase your wavelength from maybe from the 800 nanometer to around more than 1500 nanometer. So the electron can simultaneously absorb the four photon, can provide you the four photon image or the third harmonic generation. So can you scan your sample and got the 2D image? Then you move your this stage So then you can control the 3D, the imagery. Like here, we had a neuron and the level with the lucifer yellow. So you can see here, can get the 3D image. Also for the cell, so you can check the cytoskeleton, the tubulin, the 3D image here. Not just for the nonlinear optical microscopy for the molecular image, you also can use the femtosecond laser to do the 3D lithography. Like here we use the LeCosPA as the photo initiator. So when you confine your laser spot to the 3D, the scattering, then you control the laser on and off. So you can here we can create, fabricate the micro elephant. The elephant size is around the 50 micron. So you can see the nose and the teeth very precisely. So resolution can down to about 1 or 200 nanometer for the fabrication. Not just for the monomer, you polarization for the 3D structure. So for here we use the BSA or the Lamian or the fiber-lated. So you can use the two photon cross-linking to create the structure, the extracellular matrix, the biopolymer for the living cell. So show here we have use the laser and fabricate concentrate the Lamian structure. So the central part is the higher concentration. The outer part is the less concentration. So the living cell and the move from the outside to the inside. This figure you can see we have in total about 40 more in the concentration for the fiber-latin in the right side. So the living cell can move from the left to the right for the living cell the study. But like this year, the Nobel Prize in the chemistry is the people based on the nonlinear optical microscope, but they from the microscope to the nanoscope, so break the diffraction limit for the super resolution image. So the current challenge in the biomedical nonlinear optical microscopy are at least about 1, 2, 3, 4. And the first one is I just mentioned conventional nonlinear optical microscope is based on point by point scan. So it's mean right now the frame rate maybe is around 3 to 5 frames per second. But some application you need to look at the very real time or dynamic the signal, like the neural signal. So you need the very fast the frame rate for the real application. So today I will talk about focus on the temporal focusing based the multiphoton microscope. Also for the resolution, we know for the RB diffraction limit. So usually the resolution will limit by the lambda over 2. So here I will focus and show the nonlinear structure evaluation microscope for how to break the diffraction limit. For the palm or for the stone or the step, it's people the Dr. Stan Hale and Matisse, he worked on the palms and the step, so they got the Nobel Prize this year. But for the palms or the stone is for the one photon excitation. So right now in my lab, we also try to use the two photon for the stone and the palms. But for the fluorescence efficiency is quite low. So right now it's also a big problem. But this technique, pulse and the stone, is based on the wide field. It's one photon. For the stack, it's also it's a point by point, so you cannot get a very high frame rate for the real-time application. So for the stack, if people can do the like the temporal focusing or the wide field excitation, might be the biomedical nonlinear optical microscopy is more useful. Here I also show you, because the light scattering problem. So if you try to image the tissue to get the deeper information. So here we integrate adaptive artist system together. So the last part, we use the laser not just for the image, we also use the laser to cut our biosample first, then look it inside the image. Okay, so this is my outline. So first of all, I just introduce the conventional femtosecond laser system. Then so I will show you how we try to use the temporal focusing based multiphoton microscopy to do not just for the imaging, also for the microprocessing. And I will show you the current our capability. We can get the frame rate more than the 100 frames per second. So we also use the nonlinear structure illumination microscope to try to get the higher resolution, and also the adaptive artist and for lithography and ablation. So for the 2-photon or multiphoton microscopy, it's over more than about 25 years, but it's a point-by-point scan. So I just mentioned the frame rate, just a few frames per second. So it's not good for maybe for the live animal. So how to increase their throughput? So this four. The first one, the people use I saw it's Peter, so the Charles Lin use this technique for the paradigm scanner. Okay. So you can use the paragon and very fast your paragon mirror and to scan your sample. So this technique can get about frame rate about 30, got a video rate like the 30 frames per second. And also people use the acoustic optical diffractor to use the AOD to diffract the light and to scan your sample. I saw this the Peter So from the NIT. He used the multi-focus. It means not just focus one spot. Simultaneously, you can focus about like 8 by 8 the spot to your sample. So then you can use the multiple PNT array to get your signal. But for this one, and this one, the current frame rate also just about maybe 20 or 30 frames per second. So today I focus on how to use the temporal focusing base that can get the frame rate over than the 100 Hertz. So for the temporal focusing, why he can get a very high frame rate? Because he based on the wide field excitation. So then you can get a frame rate even up to about 1 kilo frame per second. But the problem, right now even you use the multiphoton, use the near infrared, but your signal you receive is the shorter wavelength. So when you use detector, not just the PNT, is the 2-dimensional array detector, then the signal will be coupled. So right now, also for the image, this spatial also still limited by the scattering of the light. Also for the temporal focusing, right now, the excitation balance is around a few micron. So also some disadvantage for this part. So if you based on the temporal focusing, so first of all you can get the better the scan, not just for the point by point, it's a wide field scattering. But if you use the conventional wide field excitation, you cannot get the result capability. So based on the temporal focusing, then it's possible use the multiphoton and for the wide field excitation. So here I show you for what the difference between the spatial focusing and the temporal focusing. The temporal focusing is you can use the high NA, the objective, to focus in your laser spot, so the pulse width is dependent on the change. But for the lateral beam size, it's a focus. So you can put a very tiny focus spot, maybe less the diameter less than the one micron. But for the temporal focusing for the femtosecond laser, so it's mean for the laser is a pulse laser here, and you have a different wavelengths and combine together and to create the pulse the laser and pulse the energy. And then you have for the grating. So grating will dispersion your pulsing light and separate the light in the space to the optical system. So finally, you can use the objective to recombine these different wavelengths, the laser, and go together and in phase. So in the focal plane, you can get the pulse, the laser come back. So it's mean in the here you have a very high density, the very high photon density. So its possibility can produce the multi-photon association in the focal plane. So it's mean in the focal plane you can get the multi-photon excitation. So for here the spot is around the diameter is around a few hundred micron. So then you can catch the fluorescence image simultaneously in the focus spot. So this is our system. So you have a femtosecond laser and use the half-wave plate and polarizer to control your laser power. And just I mentioned for the grating to diffraction your pulsing light to separate the different wavelengths, and then use objective recombine your different waves and the pulsing in the focal plane. But this set are the different to the conventional one. Conventional one, you just use a ultra-fast laser oscillator. So each laser pulse energy is maybe around 100 nanojoule. But they just excite the one spot. But for the temporal focusing, it's inside the whole area. So if you just use the oscillator, the pulse energy is not quite enough. So here we use the amplified regenerator. So this amplifier, the pulse energy can enhance about 8,000 times. So higher than the oscillator. So it's mean you can excite the area I just mentioned, say about a few hundred micron. Also here, you need a very nice the CCD. We use the ENCCD sorry. Is it on? Sorry.
不需要，那里就有电。你用我这个。
So you can see here, we also put a very nice CCD, the EN-CCD. So they can offer very high signal to noise ratio and also very high frame rate. So right now for this system setup, it's based on the high energy, the amplifier, and also for the grating, and also the very nice CCD. So we can get a frame rate up to about 200 frames per second. And the resolution is based on your objective. If you use the NA, like the water objective, so you can, the NA is around 1.0. So you can get the lateral resolution is around 400 nanometer. For the Axial resolution, it's based on your setup. It's based on your grating, the ruling density, or based on your objective, the NA. So excitation, the bar length is around 3 micron. Okay, so based on this system, because they can provide you for a real-time application. So like this microfluorescence beam, so they can provide you the Brownian motion, like here. If you use the B is around 1 micron. Okay. So the nanoparticle is a Brownian motion. When you decrease your beam size, the bit size, so then the diffusion coefficient will increase. So then the Brownian motion will be fast. So you can see this is a small particle, nanoparticle. The moving is very fast in the 3 dimensions. So it means if you are the microscope, the frame rate, maybe just 10 or 20 hertz. If you try to check the particle, the moving, the behavior, then you will lose the information. But when your frame rate up to about 100 hertz for this kind of small particle, then you can check the tracking and trace the particle moving. Okay, so this part I will show you some for the spatial resolution. That's mentioned the Nobel Prize in the chemistry. The people is work for the super resolution. So usually your resolution will limit by the diffraction. So for the lateral resolution is based on lambda over 2 times the numerical aperture. For the Axial resolution is based on the 2 lambda over the numerical aperture square. So if you use the pulse, but pulse is a 1 photon excitation. So right now can get a resolution down to about 20 to 50 nanometer. For the Axial resolution, about 10 to 18 nanometer. Also similar for the stone. But today I will focus on for the technique is structure innovation. So this system you can use a saturator or the nonlinear, then you can increase your lateral resolution. Not just the 2 times, also can 3 times or the 4 times. So then first of all I show the system just very similar the last one, the configuration, but only the different because you try to do the structural innovation. So you need a spatial light modulator, or you need like the digital micrometer device to create the pattern excitation. So here we just very simple. We use the digital micrometer device, just like the projector. We know the projector can use the projector to control the light, to create the different kind of the pattern. But this DND here is not just create the pattern, because as we know the DND just like the small mirror, and just like the bridge grating. So the bridge angle is around 12 degrees. So we use this DND to replace the grating. So this DND not just for the generate the pattern for structural innovation, they also can replace the grating, just act like the grating. And we calculate this around the functions around the 10th order diffraction. As for the grating, just like the 529 per millimeter. So the DND provide the diffraction for do the temporal focusing, but also you can localize the control the small mirror on and off to provide you the pattern innovation. So can provide different kind of structural innovation simultaneously with this DND and also for the grating diffraction. So here you can see we drop the 200 nanometer fluorescence the nanoparticle on the slide. So if you use the temporal focusing microscopy, the resolution is around 400 nanometer, as I mentioned before. But if you have the nonlinear structure innovation microscope, based on our simulation calculation, we can improve about 2.5. So it's mean for the resolution from the 400 nanometer, then right now can down to about 150 nanometer. So for this small nanoparticle is around 200 nanometer, you can distinguish the particle, the profile. So this for this one. So original the temporal focusing is based on the system, the objective NA, also based on your emission wavelength. So the resolution for the lateral is around 400 nanometer. But with the nonlinear structure innovation, and we got about 2.5 improvement. So we can get the later spatial resolution is about 160 nanometer. This is for the lateral. Also for the axial resolution, I just mentioned because the diffraction efficiency for the based on the gradient, also for the NA or your sample dispersion. So right now the original the excitation bar is around 3 micron.